So let's see where we were, right? So we were discussing this notion of the distances, right? So we end up with was we saw there was a stability result, right? Essentially, let's just quickly recap here. Right? It said that the result, right, said that the optimal value with respect to P minus the optimal value with respect to the distribution Q, right? We know that that optimal value is less than that distance, which we call the G rho, right, between P and Q. And we saw that this is less than the distance PQ, right, the distance with the Lipschitz distance, okay, the Kantorovich distance with respect to the cost function C, that the supremum over all the Lipschitz functions. And then, but the main thing that we saw, right, at the end, was this is less than the Monge-Kantorovich distance, right? Because then, the advantage, as we saw, right, the advantage of such a result is that this one we can actually calculate, right? This is just a linear optimization problem. And as we saw, in this case, we get just a linear program, right? In this case here, when you have finite support, we just have a linear program, which is ultimately what we end up with, as we'll see soon, right? For example, if your original space only had finitely many points, right? Could be a lot of points, but only finitely many. Well, this would be, you end up just with an LP, okay? So we get this bound, and then as we were discussing here, the particular case where the C function is this, right, to the power eta, this is called the Wasserstein distance of order. So in other words, Wasserstein distance of order 1 is the same as the Kantorovich distance. Yeah. Ready?
Do you have any idea when for some particular case, which is the allowance that we get from DGB?
The gap? Yeah. I haven't seen that quantified, because the thing is, right, this one actually, this one, as we saw, is an equality, right? Okay, this is just duality, right? So under those conditions that we saw, right, like if you have if C is a continuous function, for example, we know that this one is sharp, right? Is actually an equality, right? But the problem is this one, right? So this one, I mean, remember, the way we went from here to here is because the functions here are a particular subset of the functions here, right? So in general, I think this is, right, this is strict inequality, right? But how much the gap is, I don't know. I think it depends on what the function G is also, right? I think it's hard to say for a particular, for in general, what this would be, because I think the difference will depend on the structure of the function G. Oh, yeah, of course. Well, but remember, even this is a bound, right? So even if you were able to get equality here, this one is still a bound, right? So even if you get this a quantity, let's say you were able to, this is equal to whatever, 1, right? We still, I mean, this is a bound on the optimal values, right? So the way I view this is that this is a tool to motivate why, if you're able to approximate P by Q, you can actually reduce the optimal value, right? That's more, but it's not giving a quantitative bound on the difference. And this problem is very hard, right? You have to quantify how much, right, your problem changed from moving from this distribution to this other distribution. This is an extremely hard problem in general, right? That's why, the nice thing about when you can use Monte Carlo methods, that bound can somehow be quantified. Right? We have all these asymptotic normality results, right? That we have some idea. But here, there is really not much can be said, right? Because we don't know what this bound is, how loose this bound is in general. Right? True. Well, It's quantified, right? It's quantified, but it's not giving a bound, a concrete bound on this difference, right? I mean, I would say a way to measure the actual difference you have, right? You know there is a gap between VP and VQ, but this is not giving you a tool to actually measure what that error is. It just says, okay, there's an upper bound on that error. So if I make this one small, I guarantee that this is small. That's the rationale behind all this, right? So if I only need to make P close to Q, and then the optimal values will be close, which could be intuitive, but this is quantified, right? In a very precise way how that works, right?
Another intuition is that if I take that ball that you put around the origin, straight to
The row,
but if you move to the optimal solution, maybe you have a more maybe you have a more tighter.
You mean the row is smaller?
Yes. No, it's smaller.
Could be. I mean, remember, the result says that there exists a row, right? I mean, this is a local approximation. You have to remember that, right? This is a local approximation. In particular, one thing that's often overlooked in this type of result, I won't go back to that, but one thing that is often overlooked in this type of result is that this holds, but for this inequality to hold, you must have the PQ, right, less than epsilon, right? This is like doing local approximation of a function, right? It's not like this bound is globally, is valid globally, right? The bound is valid if you are close enough, right? So those are limitations of this type of result. You can only apply, if you don't have, if they're not close enough, you cannot even apply the bound, right? Because this is just local approximation. Right? That's what it is, right? It's a local approximation of the optimal value function. If you're not too close, you can't be say anything about this difference. Nothing.
The result is there exists a row such that
No, there is a row and an epsilon. There is both, right? So there exists a row and epsilon such that if this is small, then this inequality holds. That's the stability result. Okay?
Maybe I could get some global inequality. I have some properties that
Oh, yeah. No, well, the functions are already, I mean, to be able to apply these inequalities, we assumed there was some Lipschitz, not actual Lipschitz, but we, for example, one we assumed, let's see if I can find it. Where was it? This one, right? We did assume this, right? It's not exactly Lipschitz because it's a Lipschitz, but we're allowing the dependence on X, right? But it's an assumption on G already, right? For this. It's not any G. So yeah, those things have to be taken with a grain of salt, right? I mean, it's still, it's a very powerful result, right? But fairly general, but we have to remember the assumptions behind, right? And not to overlook the assumptions behind this type of results. Okay, so here's the Wasserstein distance, right? Okay, so what do we want now, right? So once we have this bound, so we know that for given P and Q, calculating the distance between them just amounts to solving a linear problem, right? Maybe it's infinite dimensional if it's infinite many scenarios, but if it's finitely many scenarios, you know it's only a linear program, right? So calculating the distance now is an easy thing to do. Okay, so then but of course our question is not really the distance, right? What we want is to select the scenarios, right? So what do we want? What's the idea then? Say, okay, so P is known, so we start with the distribution that we know, right? And I want to find a Q that has fewer scenarios, right? Fewer scenarios than P, and it still approximates well, right? So we can think of Q being sort of a smaller than P, right? We have the P as the original one, then we want to find the Q that makes this, or this one, small, right? So if you think about, right, going back to the Monge-Kantorovich problem, right? If you think about this one, essentially what we want, right? It's like we want to find the t's and the pi's, both, right? So if you try to do them at the same time here, then the problem is not so nice anymore, right? I mean, if the t's are fixed, right? If you fix the support, if you just want to find what's the distance, it's a linear program. But if you want to find the t's as well, so okay, what are the scenarios that give me the minimum distance? Then, well, now this is a much more complicated problem, right? Perhaps even non-convex, right? Because we have this function. Imagine that this c function is the norm between s and t, right? So then your objective function will be like the norm of, you know, si minus tj times the pi, right? Well, but this is a variable and this is a variable, right? So this is not as nice problem anymore, right? So that's the, but still, it's an optimization problem that can be posed and one can try to solve, right? And then we'll see what we can do about that. So let's first think of the easy case. Let's suppose we fix the support, right? So I fix the values of the y's, right? So let's call the y1 to ym, let's call that the support of Q, the scenarios that we want to find, okay? So if I fix the support, then, of course, this is just an LP, and turns out we can even solve that analytically, okay? It's very easy, right? It's just like this, the solution, right? You just look at the set of the indices of the ZJs, or the ZIs, that are closer to NI, so it might be easier to see a picture, right? So imagine those are your Z scenarios, right? And here are your Y scenarios, right? So this is P and this is Q, right? So in essence, this is saying, okay, look at the one that is closer, right? And then you just associate these guys with the one that are closer, like this. That's what the solution is, right? And then the probability here is just the sum of the probabilities of the corresponding piece. That's what it's boiled down to, okay? So that's the solution of the LP. It's very intuitive, but that's exactly what this LP will give, right? So the pi ij is just the pi I, right? When the i's are in this set, right? Which are the closest ones to that point. And then the q's are just the sum of the pi's that are the closest ones, okay? So if we know the support, calculating the probabilities is very easy, right? It's just, just this calculation here. You don't even have to solve the linear program. But what if you don't know the y's? That's where things start getting complicated. As we saw, right, we get a non-convex problem. But one particular case that is helpful, if you assume that the support of Q is a subset of the support of P, right? So you say, okay, I'm starting with all these scenarios here. I want to find what is the subset of them that has minimum distance. That's easier than finding, like in this case, right, that we can find a scenario here that is not one of the original ones. Right, you see that? Right? So if I restrict my Q to be a subset of P, at least now I have a combinatorial problem, right? So it's like, well, what is the best subset of the P that makes the distance minimal? Then it's a combinatorial problem, right? And this is called a scenario reduction problem. Why is a scenario reduction? Because we're starting with a certain set, and then you want to find a smaller set, right? You want to find a subset of that problem, and that has minimum cost, right? Minimum distance. So this is called the scenario reduction. So the problem is combinatorial. And so some alternatives are, well, one can do, it still is a difficult combinatorial problem, right? That doesn't mean, the fact that it's combinatorial doesn't mean that it's trivial, right? I mean, on the other way around, I mean, it's still a hard combinatorial problem. This is called, by the way, a facility location problem, okay? But there are some easy cases that are easy to solve, right? So for example, if the support of Q, is 1, if you just want to find one scenario, right? You have a collection of P, you just find one that minimizes the distance, that's easy, right? Because if you just find one, it's just like it's an order n algorithm, right? You just wait to find which one of these n scenarios in P gives the total, has the smallest total distance to the others. Just an order n algorithm, it's easy to solve. Likewise, if you assume that support of Q is everything but 1, then it's just like, okay, which of these should I throw away, right? I want to keep n minus 1, which one I throw away? Again, it's an order n type of algorithm, right? You just figure out, okay, what is the one that is the farthest? I'm going to throw that and keep the other n minus 1. So those are the easy cases. The cases that are harder, of course, is when you have the support is like more than 1 point, right? Because now you have combinations, all the combinations of 3 points, all combinations of 4 points, and so on. But if you have 1 or n minus 1, then it's easy. So that gives rise to some heuristics, right? So that's called, one is called the forward heuristic, and the other is called the backward heuristic, which is sort of a greedy way of doing this, right? So imagine that you start with an empty set, right? And then you say, okay, I'm going to start with an empty set. I want to select my Q here, right? So I'm going to start with an empty set and see, okay, what is, if I had to choose one, what would that be? Let's say then this one comes out of the solution. Now, okay, then we forget about this one and look at the remaining ones and say, okay, now what is the one scenario that best represents whatever is left? Okay, then suppose, I don't know, this one comes out. Then you add to your set. And now you do the same thing. Okay, now what is the best one that represents everything else? And then you keep going until you reach the number of scenarios that you want, right? You want to reduce set. You just keep adding that way. Okay, so that's a very intuitive, but it's a heuristic, of course. This is not going to give the optimal, right? Because you're doing a greedy type of algorithm, right? You could also do the other way around, right? You could start with the whole thing and drop one by one, right? Because that's easy to do until you reach the number that you want. But again, those are heuristics, right? You have one solution here, but it's not necessarily the optimal solution. But this is something that is implementable, very easy to implement. Okay. Another option, of course, is trying to solve the combinatorial problem, right? You can model this as a facility location problem, right? So what is a facility location? That's a problem that's a well-known problem in combinatorics, right? Where you have it's like you have many cities here, right? And then you want to find where to place, like I don't know, like a store, right? So you want to put two stores, right? So you have all these cities here, and you want to open two stores. Well, where should you put those stores? Well, maybe here, right? No, maybe you want to put one here and one here, right? Well, how would you choose the location for these stores? Well, you don't want to be too far, right? You don't want to be too far from other people, right? From all the other cities. So maybe you want to find the two cities that minimize the total cost, the total distance to your customers, right? So that's what this is called a facility location problem, right? Where to put this? So it's a well-known problem in combinatorics. It is a combinatorial problem, and there are many ways of attacking, right? Of tackling this problem. One of them is modeling as an integer program, right? So there are many ways of doing this, but it still is a combinatorial problem. We can get away from that. Okay. One complication here, right, is that it's a mixed continuous integer problem, right? Because you have the locations are discrete, but the continuous values are probability. So if you try to solve all of them together, this is like a facility location, but it's a mixed integer problem. So it's still doable, but maybe not in very large numbers, right? You can only solve relatively small problems. Also, this is k-dimensional, right? Remember, we are not talking one-dimensional points here, right? So this is each point here is actually a k-dimensional vector, right? Because that's the size of the uncertainty, our xi, right? Each point here corresponds to a xi in our problem, right? So each of them is a vector in our case. So that's another complication here. So there's one paper, for example, by Dempster and collaborators, where they propose kind of iterative scheme, right? So, okay, minimize the y's, find the pi's, and then minimize the y's again, find the pi's, right? I mean, if you remember that problem where the y's are the points and the pi's are the probabilities. So they kind of do an iterative scheme. It's a heuristic also, because there is no guarantee of optimality, but it's something that was proposed. Then a very recent paper by Flug and Pichler, they studied the problem from a slightly different perspective. And this is also, I find an interesting approach, which is the following, right? So suppose, right, that, this is the space where the random vectors lie, right? It's a subset of Rk. And then let Y denote an array of m points, which are the candidates to be the support. Now we are allowing the Y's to be, not just to be a subset, right? Now we are allowing the the support of Q to be anything. Right? We want really to find what are the points, the scenarios, not necessarily the subset. So we are outside the combinatorial context. Okay, so how to find this, right? So given a scenario, so they define, let's define this D here, nothing to do with the Ds that we saw before, right? They just, it's a different notation here, just the distance between C and the element of this set, which is the closest to C, right? So imagine that I have a candidate set, right? So this is my candidate set, the Y1, Y2, right? I have some candidates here. Those are the candidates to be the support, to be in support of Q, right? The selected scenarios, okay? So, and that's so we're going to look at, for a given value of C, right? For a given scenario, we say, okay, I'm going to look at the scenario. This is my C. What is the scenario? What is the point in the Y set that is the closest? Well, in this case, maybe it's this one, right? If the C was here, this would be the closest one. Okay? So that's how we are defining the distance, right? In a sense, between C and this set is the distance between C and the closest point in the Y set. Is that clear? So the Y is the discrete set now, right? Which is a subset of the larger space, right? So we have a larger space here, which is our where our C is, right? This is our set of possible, this is a subset of RK, right? That's where our scenarios could be. So we are taking this point as candidates, but our actual scenarios could be anywhere. So for a given scenario, just measure the distance between C and the Y's, right? So this is a number, right? Just the distance between the C and the set. Well, now define this function, right? As a function of the Y's, right? So the Y here, I mean, this is actually a matrix because it's a vector, but each vector here, each Y is actually a point in RK, right? But still, one can define this function D, right, which is the expected distance between C and Y, right? Where C, well, we know the distribution of C, so this quantity is well defined, right? It's like, what's the average distance between a C and this point set? Okay? So that's a D of Y. So what do we want, right? We want to find the Y that minimizes this function, essentially. Right? We want to find, that's one criterion, right? We want to find what is the set of points that makes this average distance the smallest possible. Is it clear what we are doing, right? So we are just essentially taking this point set here. For each scenario, we calculate the distance between the scenario and the set, this Y set, right, which is just this finite set here, and that's the distance to the closest point. So if this is defined for each C, well, we can compute the expected value of the distance. So the set Y that gives the smallest distance, right, is that's the one we want, right? To minimize so it will be this. It will be always a collection of m points that gives the minimum distance, minimum expected distance. And you can say, oh, that sounds a very complicated problem to solve, right? Yeah, it is. However, they show that in this paper, right? They show that when C has continuous distribution, turns out that this function is differentiable, and one can actually estimate the gradients of this function. So you could do a sort of a first-order minimization method on this. They're not necessarily convex. Problem is not convex, but you may have at least like a stationary point, right? Remember, all these problems are very complicated, right? So anything one can do helps, right? It's a combinatorial problem from one hand. Here's a non-convex problem from the other hand. But, you know, at least you get some local minimum here, right? It turns out one can actually estimate the gradients of this function. So that's what they do in this paper. Okay? Is that clear so far what we're doing, right? So essentially, all we have done is studying the situation where we have this distribution P, and how do we find the distribution Q that somehow we try to make this distance small. Right? You're trying to minimize this distance. And Q, and we're essentially imposing restrictions on Q, right? You're saying, no, I don't want Q to have more than M points, for example. right? Because I want to find a small distribution, right? That I can, it's an approximation with few points. So we are imposing constraints on Q. If you didn't impose any constraints on Q, of course, you just say Q equal to P, right? Q equal to P is not fun, right? But here, essentially, you say, okay, I want to take the Q that makes distance small, but Q has, it's a limited size. Like here, right? You're fixing, you're saying, no, I can only have M points at most. No, M equal to 20. I want to find only 20 points that approximate my whole distribution. Okay? But that's for a particular, that's for one, right? You can think of this as a single stage problem, right? Given a distribution, we want to approximate that distribution, right? Well, but now we want to talk about dynamic problems, right? Stochastic dynamic problems, which are very much used in practice, right? And here's some examples, right, of dynamic problems. Like, for example, people at ONS deal with this problem every day, right? The hydroelectric planning, right, is a multi-stage problem where, okay, how much energy do you produce and store, right, in each month or each day, depending on the horizon that you're looking at, right? But for example, the hydroelectric planning, well, the uncertainty comes from the water inflows. You don't know how much is going to rain, right? And how much energy do you produce and how much you store, right, in the reservoirs. That's a classical problem, right, that people have been studying for many years. Many approaches have been proposed, but it's a dynamic problem. It's stochastic and it's dynamic because you have a planning every month, right? Finance also, these models, these dynamic problems are very common in finance, right? It's like, okay, how much money I should put in my investment every month, right? I don't know the returns, but I want to put money every month and with some goal, overall goal, right? Maybe I want to minimize, the money at the time of retirement, maximize my money at the time of retirement, anything, right? Maybe I have some goal, or I want to maximize my consumption every month. So, but that's also a dynamic problem, right? Because you're reviewing your investment strategy every month, for example, right? Revenue management, right? For example, this is also used a lot in airlines, right? So which fare classes you make available, right? You don't know, people are booking the flight, right? So you don't know how many, which ones you make available at every point in time, right? So there are cheaper fares and there are more expensive fares. So which of them should you make available, right? Because if you make all the cheap tickets available initially, people are going to buy, and then you have nothing expensive left, right? All the business travelers that are willing to pay more, there'll be nothing left to them, right? But you reserve too many, you say, no, I'm going to keep all these seats. I'm hoping for these expensive customers that will come later. Well, maybe they won't show up, and then you end up with an empty flight, right? So that's the typical problem that airline companies have, right? In any flight, they have to do this. Well, it's a dynamic problem, okay? And stochastic because you don't know how many people are going to come and how much they're willing to pay for the tickets, right? So all these problems fall into this general framework, right, of stochastic dynamic problems. And then, well, the connection with what we are doing here is, well, how to generate scenarios for these problems. Right? We want to solve these dynamic problems. You need to generate scenarios, right? Typically, the same here. The approximation problems are even worse, right, than in our original problem, because now we have to have scenarios that are over time. How do we generate that? So that's what we want to discuss from now on, right, to the rest of the lecture, what to do in the dynamic case. Is that clear? The goal? Okay. So you can think of the dynamic problem, right, in this way, right? So you make a decision, you observe the uncertainty, and then you make a decision, right? In 2 stages, that's it, right? A 2-stage problem, that's it only, right? You make a decision, observe the uncertainty, and then make a correcting decision. This is something called the recourse decision, right? And that's it, right? So you guys have seen this in your stochastic optimization course, right? So in 2 stages, things are much easier, right? Because there's only one source of this uncertainty here. And then, well, if you generate the scenarios, that's it, right? But in the T-stage case, well, this is an iterative thing, right? You make a decision, you observe the uncertainty, you make another decision, you observe more uncertainty, right? And so on, right? Until the final point in time here, right? So this makes a much more complicated problem, generating scenarios here, right? Because now you have to figure out a way to generate the scenarios for XC2 and XC3 and XC4, but there is this dependence chain going on, right? It's not just like those are separated problems. Right? You cannot, this problem and this problem are completely independent. No, they are connected, right? Because whatever you observe here affects what you observe here, right? There's correlation between these random variables. So this makes the generation of scenarios in the dynamic case a much more complicated problem than what we saw here. If this one was already complicated in a sense, right? We're giving up all these, non-convex problems and so on to select the scenarios. Well, now we have an extra layer of complication, which is this temporal dimension to the problem. But those problems are needed, right? One has to solve this to be able to use multi-stage problems. And in practice, they do something, right? For example, in the electric planning, well, they have to generate the scenario somehow to be able to solve the problem and come up with a planning. Okay, so let's put this in the framework of multi-stage models, right? So, of course, there are many approaches to do stochastic dynamic problems, like Markov processes, approximate dynamic programming. There are many types of tools, but here we want to focus particularly on the case of multi-stage stochastic programs, right? Which can be formulated this way, right? You can think of it to have the expected value of functions that are a sum of functions. So you have, this is like your cost function in each period, right? So you have an F1 that depends on the decision that you make in that period and the uncertainty, right? So this is your total cost. What are the constraints, right? So every point in time, your constraint is that its x belongs to some set that depends on the previous decisions and the uncertainty that you observe up to now, okay? So remember the graph here, right? So whatever you decide here can only depend on x1 and x2. What you decide here can depend on x3, x2, x2, and x1, and so on, right? You can only, the information, the decision that you make at time t can only depend on what you have seen so far, right? You cannot be, you don't have a crystal ball, right? To look into the future. So your decision today can only depend on what you have seen so far, right? Demand or the water inflows, whatever it is, okay? So the x are the decisions, right? The x is the uncertainty observed just before time t, okay? So you can think of x1 is a constant, right? In this picture here, there's no x1, right? So you can think of x1 is what comes before x1. Well, that's just a constant. There's nothing random about that, right? So the first uncertainty that you observe is x2. That's just our notation here, okay? So F is the cost, right, as we mentioned. And this xt is just the feasibility set, right? And the feasibility set depends on the previous decision, the observed uncertainty. And also notice that we have this constraint here. Well, what this means is that xt is, so this sigma, x1, xt, you can think of this as, right, it's the sigma algebra generated by these random variables. You can think of this is the information observed up to time t, right? So xt can only depend on the information you see up to time t. That's what this constraint means, right? This is the constraint set, but this is saying that, well, I cannot make, my decision cannot look into the future. It's a no-anticipativity constraint. That's what's called, okay? So that's the kind of the general class of multi-stage models, right? So, for example, in the particular case of linear multi-stage models, one can also write this as a recursive formulation, right? Where you have here, in the first stage, you minimize the function with the linear constraints. So this is your cost function plus the expected cost from time 2 on, right? And then the function here, the cost function, you define recursively, right? This is sort of a Bellman type function where you have your cost function at time t, which depends on your decisions, and the uncertainty up to time t is the cost at that period plus the future cost, okay? Given, right? This is a conditional expectation, right? So this is given what you have seen so far, okay? And then you have constraints. Well, the constraint is on t, right? T is the variable of this problem. Xt is the variable in this problem. And it could depend on the previous x's, right? Up to xt minus 1. So, but those are given. When you solve the problem in time t, those are given already. Okay? So this is like it's a recursive formulation of this problem here. Okay? This can be written this way. And you can see the uncertainty here is everything that is, could be, right, the matrix A, could be B, could be this matrix B here, could be the C vector. The uncertainty could be everywhere, okay? So this is a general kind of form of linear multi-stage stochastic programs. But remember, our goal is to generate the scenarios for this problem. That's what we want, right? So how do we generate scenarios for this multi-stage problem? Okay, so let's understand what is so different, right, about this multi-stage case compared to the, say, the two-stage case we saw earlier, right? So why is it so hard, right? So we had seen these approaches, right, like the facility location. We had seen Monte Carlo methods. Well, why can't we just apply, right, all that stuff here? I mean, after all, this is just a function. If you look at this formulation, well, this is just a function of xi, right? In principle, we were calling this a g function before, right? But why? What is different about this, right? So here is here's the problem, right? So can we apply? Well, yes and no, right? Why is that? So let's see, right? So the answer is, well, you can, but you have to be careful. And why? So roughly speaking, the issue is that, right, the scenario generation have to incorporate this dependence, right? That's remember we discussed this when you look at this graph, right? Say, okay, when you generate the xi3, this has to somehow take into account the values of xi2. You cannot, it's not completely separate, right? So let's say, for example, suppose you do SAA, right? So let's suppose you want to do SAA in that problem, okay? Remember, SAA was just to replace the function, the expected value, right? By take samples, replace the expected value by a sample average. That's it, right? So suppose you look at this formulation, right? I look at this formulation here and say, okay, I want to apply SAA to this guy, okay? So how would you apply SAA? Well, now instead of having, you don't have just a xi2, right? You have a whole process, right? xi1 to xt. And then you could say, okay, I'm going to just sample from this process, right? You can think of this being a vector now, right? From xi1 to xt. I could sample from this vector and take the average, right? So that's how we do it, right? I take samples of this process, right? Let's call them xi2j to xtj, right? Take n samples. Same thing we did before, right? And then approximate the expectation with the sample average. Right? That's what we did, right? Approximate the expectation with the sample average. But let's see what happens, right? So it's like we are replacing this Q function with a sample average. Is that clear? Right? So, but let's think about, right? What does it mean to replace this with a sample average? So now instead of calculating, right, we are replacing this we are replacing this quantity, right, the expected value of xi2, right, of x and xi2, right? We are replacing this as sum. Or, in fact, I think it might be easier to think of it might be easier of thinking in this context, right, in this formulation, right? So we are essentially replacing, probably easier to do this way. You could think, well, okay, I can just take a sample, right, of the xi1s. I take a xi1, right, xij, xi1 up to xtj, right, from j1 to n. And then I just calculate 1 over n, the summation of f, x1, xi1, plus f1. Well, this would be like j1, right? Then f x2, xi2j, and so on, right? And take the average, right? Just replacing the expected value with an average. That would be what the SAA approach to this one. So, but what would happen, right, in this case? So let's see, right? So let's take the case of 3 stages, right, to illustrate. Right? We'll see if you see the problem with 3 stages, then we understand why with more stages it only gets more complicated, right? So think about, right? So let's look at this function Q2, right? What happens to this function Q2? Well, function Q2, right, is given by the minimum of, right, in this case, would be the minimum of a C2. Notice that's a J now because the C is random, right? There's randomness everywhere here. So a sample, the J sample here corresponds to 1 sample here, 1 sample here, 1 sample here, right? So the problem at time J, or at time 2, for a given sample, it would be just like this, right? I take the sample, for that sample, I solve this problem. And but the definition of Q2, right, that's the minimum of Cx plus the expected future cost given the present, right? That's the definition of Q, right? That's the definition of Q2. Remember, right? This is just the minimum, right, of the cost in the current period plus the expected future cost. That's what the function is, right? But what we are calculating, actually, when you do the sample average approximation, well, we are not doing this expectation, right? Remember, we are doing one sample, right? Xc2 to Xtj. So in essence, what we are, instead of calculating this, what we are calculating is the minimum of C2 plus the Q function for the sample for Xc3. So in other words, we are replacing this expectation with this, right? That's what we do when you're doing the sample. We are replacing this, everything, the Xc3 with this, the J sample of Xc3. But what is the problem? So how do you compare this one with this one? Do you see any problem? You know, instead of calculating this, we are actually calculating this, right? So compare these two problems. What is the difference between them? Huh? Philippe? Uh-huh. A sample, right? So here we have the expected value of the Xc3s, but here you have one sample, right? So in other words, it's like we are changing by, right, estimating our expectation, this inner expectation, right? We are changing this inner expectation with a sample of size 1. That's very bad, right? You cannot estimate, right? Imagine, it's just like doing estimating a whole average with just one sample. Of course, it's going to be a very poor estimate, right? So that's the problem here, right? We cannot, when you take samples from the process, right? This is what's going to happen, right? So you only have one value of Xc3 here. So yeah, instead of having the expectation, you have to use your Xc3j. So instead of doing this average, you have only one sample. It's a very poor estimate. So you can see that this is never going to be, right? So we are replacing this expectation with this sample of size 1. Well, Xc2j is given, right? So we don't have to worry about Xc2j. But the problem is Xc3 here, right? This is an average of Xc3, which we are replacing with the sample of size 1. So there's no way you can obtain consistent estimators, right? Even if you take n going to infinity, it's not going to help, right? I mean, you could take n going to infinity. This problem is always going to be present. You just have more Xc2s and more pairs, Xc2 and Xc3, but this problem, right? This problem here is always going to be present. Right? So just taking the sample size going to infinity, I can take as many paths as I want, right? I still have very bad estimators. So it doesn't work. That's the bottom line. Okay? So how can we fix this? Think about it. Right? If we identified that this was the problem, so how could we fix this? In terms of sampling, right? So how do we have to sample to fix this problem? Yeah. So for each value of Xc2, you need to have many values of Xc3, right? So if you have, like, for each possible value of Xc2, right, you have your samples here, right? Xc2, 1, Xc2, 2, Xc2, 3. For each one, you have to generate a bunch of them, right? So that's how you get, you can get approximating this. So for each value of Xc2j, you need a bunch of Xc3s that can approximate this expected value. That's the problem. So you cannot take just one sample of each path. So, and that's what is called, well, you can do that through, that's conditional sampling, right? So for each value of Xc2, I generate n samples of Xc3. But for each one, right? So for each of them, I have to generate another n of Xc3. And then for each value of Xc3, I have to generate n Xc4, right? You see, I have more stages. So you see what's the problem, right? We have of course, then we have to draw n square samples, right? So if you do this for a t-stage problem, well, that means you need n to the t minus 1 samples, right? That's not very practical, right? So what is it saying, right? So is that hopeless, right? I mean, the problem. I mean, but if you really want to have consistency, that's what you would have to do, right? If you want to ensure consistency, that's what you have to do. To do this conditional sampling and take n to infinity, then you can guarantee you're approaching the optimal values to get the same kind of result we saw earlier, right? But that's, yeah, of course one can do that, show theoretically that this works, but in practice, I mean, no, it's impossible to draw this number of samples, right? It's not practical. So what we have to do, the best we can do, right, computationally speaking, is work with a fixed tree structure, right? Say, okay, no, I have to limit the size of my tree. I cannot just keep, writing, taking as many branches as I want. I will work with a fixed tree and try to do the best I can with that structure, right? Let's say, well, I can afford, I don't know, 10 nodes per stage, right? Okay, if that's what you can afford, try to do the best you can with 10 nodes, right? That's how kind of the approach we did here, right? Say, okay, we fix the number of points and try to find the best combination you can of m points, right? But you won't have this asymptotic consistency because, yeah, in practice you cannot reach that. So you can see why this multi-stage business becomes much more complicated. Yeah, Philippe? No, they cannot be fully independent, right? Because there is dependence. If you think about the true process, in the true process there is dependence, right? If you imagine that for each value of C2, right? In the true process there is dependence. The value of C3, right, that you see here may depend on the previous values. So you cannot just sample them independently, right? So that's what makes this thing difficult, because you have, when you do this generation, you have to take the dependency structure into account. So like in this case, right, for every possible value of C2 that you generate, you need to generate a new sample. And this new sample here, these guys, in general, are not going to be the same as this, right? Because this is conditional on the observation that you saw. You see, that's what makes this hard, right? Because you have this dependency structure behind. Now, in the particular case we are independent, and we're going to talk about that soon, in the particular case where the random variables at each stage are independent, then it's much easier, of course, right? If the C2s, if there's no actual dependence between these random variables, right? What you observe in period 3 does not depend on what you saw in period 2, then it's much easier, because now you can generate them independently, right? And then it's a far easier problem. But the problem here is that you have to do one sample for each possible value of C2. So for example, right, how would you generate these samples? Here's one situation that arises often in practice, right? Suppose your stochastic process is given by this, right? Your uncertainty at time t plus 1 is a function of what you saw here and some noise, right? For example, this could be an autoregressive process, right? Autoregressive process is the one where you can write the uncertainty at time t as a linear combination, right? It could be your ct plus 1 is like a1 x1 plus a2 x2, right? Plus at minus at, I'm doing t plus 1, right? So at ct plus some epsilon, right? Where this is a noise. This maybe has like normal distribution, right? This is autoregressive process, right? So your uncertainty at time t is a linear combination of the values that you saw in the previous periods plus some random noise. Right? It's a classical model in statistics that people also use a lot to model, for example, the water inflows, right, in the electric problems. So there's a particular case, right? This is more general. We're just saying, okay, we could have could be perhaps even not a linear function, could be a more general function of the previous observations and some random noise here, right? Could be some uniform random vector, could be normal. The distribution here doesn't matter, right? Important that this noise is independent of everything else, right? So in that case, doing this Monte Carlo sampling is very easy, right? Because all you have to do is generate a bunch of U random vectors, right? So here's an algorithm, right? So suppose this is the number of branches to be generated at each stage, right? You fix, right? You have to work with a fixed tree structure. So for each T, well, you just generate a bunch of uniforms here, right? You could use Monte Carlo. You could use the quasi-Monte Carlo method, as you know, that Güzin described on Wednesday, right? You could do even quasi-Monte Carlo for this use. And then for each T, right, I'm going to generate the children of these nodes. Right? For each node, I'm going to generate the children using this relationship, right? Because for each given value, I just apply this psi function with the U that I generated, and I get samples of ct plus 1. That's a very natural way, right? So you only need to sample from uniforms. That's all this boils down to, right? And those are uniform random variables. That's very simple to do this. So doing the sampling here is actually very, very easy, right? If you fix the tree structure, it's very easy to generate the tree with that dependence structure, okay? So that's the case of sampling. Okay, how about then the those distances, deterministic scenario selection that we saw earlier today, right? Remember we saw that for the single stage problem, we could do random sampling, but we could also do this scenario selection, right? That minimizes the Monge-Kantorovich distance and so on, right? So how does we can do that here, right? We are looking, well, we are revisiting those concepts now in the context of multi-stage, right? So we saw how to do the sampling in the multi-stage, and now we want to see how do we do the distance business, right? The probability matrix distance in the multi-stage case. Is that clear? The goal? Any questions so far about the random sampling in the multi-stage case? Okay. So. Okay, so let's consider now this input process, right? Now, notice that I talk about the process, right? Now it's not just because remember now we have X1, X2, all the way to Xt, right? So we have talk about the stochastic process. And let P be, well, we'll see why I'm putting distribution here in quotes, okay? We'll come back to that issue in a second. But let's suppose this is kind of some way to measure the distribution of this stochastic process, right? So as before, our goal, right, is to find another distribution of this some process here that approximates P and has fewer scenarios, right? But now all in the multi-stage context, right? So we have to think of the distribution of the whole thing now across time periods, right? So one way of think of this is that, okay, I have an original tree, right? This is my process. This is my original process, right? I can have many branches, right? And then here I have many branches, right? And I want to find a smaller process that, maybe with only two, right? Has smaller, much smaller number of scenarios, but still approximates the big process. That's essentially the goal, right? So this will be our P, and this will be our Q, right? So how can I find this Q that still represents my P, right? Well, but it's a much smaller tree. That's essentially the idea. Okay? So how can you do that, right? So first, we come back to this issue of the distribution, right? When I said, well, distribution, quote and quotes, well, why do we put this in quotes, right? So let's think, well, what is the distribution of Ct? Right? One can think, well, Ct is just a stochastic process, right? C1 to Ct. Well, the distribution of a stochastic process, this is a very well-defined quantity in probability, right? How do you define, in probability, how do you define the distribution of a stochastic process? Those of you who have taken stochastic processes, how do you define the distribution of a stochastic process? fix? Yeah, but you have to look at all combinations, right? So more generally, you could say, well, I have to compute this probability, right? C1 in A1, right? And I don't know, I fix A1 and A3, right? I have to be able to calculate this, right? But you have to do all the combinations. So more generally, this means, well, because this is finite dimensional, this means that I would have to know this, right? For any, right? A1, A2, AT, any sets, right? I have to look at, in other words, I have to know, we have to figure out the joint distributions, right, of all T random variables. So if I can do this, the process is completely specified, right? Because essentially, you can think of this as being a random vector, right? So I'm specifying the joint distributions, all possible joint. If I know the joint distribution of all T, I know all subsets, right? So in probability theory, that's how you specify the distribution of a process, right? This is a finite horizon process, so you just have to specify the joint distributions, and that's it. Okay? Well, so does that work here, right? So we just specify this, right? So for any measurable sets. But is that good enough for us, right? So so here's where, again, getting to the multi-stage business starts bringing some surprises, right? So this is an interesting example that comes from a paper by Georg Flug, okay? I got the figure from that paper. So look at this process, right? Imagine, so this is, think of this being well, our C1 is always a constant, right? So imagine this is C2, this is C3, and this is C4, okay? Same thing here, C2, C3, C4, right? So C2 turns out to be a very simple random variable, which is equal to 0 or 0, okay? There's nothing fancy about it. C3, the same thing, right? C3 is only 0, 0, 0, 0. And C4 is, the values will change based on this, right? So if I fell here, well, there's 1 or 1. So if I fell here, it's 1, 0, and so on. Okay? And now consider another process, which is given by this, right? This tree structure here, okay? So, what can you say about the distribution of these processes in these terms? Think about, right? Compare this to this. For example, what's the probability what's the distribution of C2 in this tree here, for this case? C2 is just 0, right? With probability 1. How about on this side? Same thing, right? Here, C3, the same thing, right? C3 is 0 with probability 1, 0 with probability 1. How about C4? What's the distribution of C4? Half of the cases is 1, half of the cases is 0, right? But here's the same, right? Then you can say, okay, yeah, but those are just the marginal distributions, right? Well, let's look at the joint distributions. Well, what happened to the joint distributions? Right? Well, these guys are actually constants, right? C2 and C3 are constants, so the joint distribution is not really playing much of a role, right? So the probability, if you do this for this case, well, because the C2 and C3 are actually the same, the joint distribution is just a distribution of C4, right? But it's the same, right? Here and here, we just saw that the distribution is the same. So what is this saying, right? That these processes, they have exactly the same distribution in this according to this definition, right? In terms of probability distribution, as the way, right, in probability theory people define distribution of processes, they have the same distribution, right? Probabilistically speaking, this is equal to that. There's nothing, right? If you just look at the probabilities, yeah, they are indistinguishable, right? They are the same process, okay, from the perspective of probability theory. But clearly they have different structures, right? The tree structure here is different from the tree structure. Well, why does that matter, right? Well, let's consider this problem here. Right? Now, let's suppose I'm looking at this tree, but let's consider this problem, right? Where I want to minimize the values of x1, x2, and x3 of this quantity here, right? x1 minus xc4, right? Remember, this xc4 is this column here, plus x2 minus xc4, plus x3 minus xc4, and the only constraint is that x has to be what's called adapted, right? So I cannot define the x1 before knowing x4, right? I don't have a crystal ball. That's what this is, right? This is to say, I don't have a crystal ball constraint. That's what it is. So think about, let's do the first case, right? How would you choose x1, x2, and x3 to minimize, right, the sum of the difference between x and xc4? Whoops. This is xc4, so I want to choose x that minimizes the distance to xc4, right? Let's see. Let's try to do visually here, right? How will you do that? So looks like here we have, right? I have 1, 1, 1, 0. Here I have 1, 0, 0, 0, right? So if you were to minimize, how would you put it? Try to guess a solution. What do you think? You're trying to minimize the difference to the x's, right? To xc4. And your x has to be chosen before you know the realization. But you can pick an x here, x here, x here, right? X here, 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 and here, right? You can choose x1 is here, right? So you can pick one value for x1, 2 values for x2, and 3 values for x3, right? How would you pick if you want to minimize the difference? Think about it. So suppose I had 1, 1, 1, 1, 1. If I had 1, 1, 1, 1 here, how would you pick? If you had like 1, 1, 1, 1 and 0, 0, 0, 0, what would you do? Huh? Just put x equal to 1 on the top and x equal to 0 on the bottom. That would be easy, right? Okay, but now we don't have completely ones and zeros. We have this 1, 0 here, right? Still, what happens to the solution when you had 1, 1, 1 and 0, 0, 0, 0 here? What's the distance in that case? Right? So we are doing this, right? 1, well, we don't know x1, right? But here we have 1 and then 1, 1, right? And then we are, this is our x, right? Like this is x2 and this is x3, right? And here is our process, right? Is 1, 1. This is our xc here, our xc4. 1, 1, and 1, 0, right? What is the total distance here? If I put x equal, say I put x equal to 1, right? What is the total distance? Like 1 minus 1, 0, right? Plus, here the distance between this one is 0, 0. Here the distance is 1, right? The distance between this one and all these 3 is 0. And here is 1, right? And here the distance is also 0 to all of them except this one, right? So, but this scenario has probability, what? Half times half, this probability 1.25, right? So if you calculate this, the value of this solution, you see that you get 0 except when you have this term here, right? Except for that, except for this branch here. So if you had 1, 1, 1, right? They would all be 0 except for this guy, right? But then you have to consider what happens to the x1 here, right? So you have the x1 could be 1 or 0. So if this was 1, well, you have to discount, not count here. But if you had, so if this is 1, the distance between this guy is 1, and this one is 0. But if you had a 0 here, this distance is 0, but this is 1. So if you do the calculation, you see that the solution where you have, x equal 1 here and x equal to 0 everywhere here, that solution will have an expected value of 1, okay? Because you get is this 0.25 showing up for in this calculation. Remember what we wanted is to do this, right? So there will be oops. When you calculate that solution, you always have to consider the distance that will show up here, okay? And then what happens with we have 0 or 1. So you get a distance that has value 1. But this one is easier. What is the distance here? Let's say this solution, 0, 0, 0 to this one. What would be the distance in this case? Right? So now you can see that this is like each of these guys is contributing. Like if I put a 0 here, well, one of them had the distance is 1, the other distance is 0, right? Here the distance 1 is 0. So each of these scenarios is 0.0125, right? So no matter what you put here, you always get 4 cases wrong and 4 cases right, right? So you have 4 times 0.125. This is 0.5. Same thing here, right? No matter what you put here, you're going to be right half of the time and wrong half of the time. So there's another 0.25 there, right? Or another 0.5, sorry, because it's 4 times this. And no matter what you put here, again, you're going to be you're going to be right half of the time and wrong half of the time. So the total amount here is, what's the optimal value then for this case? Or no, what's the objective value for this case, for the 0, 0, 0 case? What? It's 1.5, right? Because we saw that's 0.5 here, 0.5 here, and 0.5. So but that's nothing special about the 0, 0 solution, right? Any solution that you pick is going to be the same, right? You always have 50% of chance of getting it right, 50% chance of getting it wrong, because ultimately this guy is totally independent of what happened before. That's what it is, right? So, I mean, you can do the calculation later. I encourage you to do the calculation later, but you can see that for the one on the left, if we put 1, 1, 1, 1 here and 0, 0, 0, we saw that we can get an objective value of 1. And here, the objective value is 1.5. Okay? So what is this saying? That although these two processes, they were probabilistically identical, when you try to solve this problem, they actually give different solutions. That's the message, right? So even though we started with two processes that are identical from the probabilistic perspective, but the solution of the optimization problem was different in either case. Why is that? What caused the problem? What caused the difference? If you compare, why we end up with different solutions here and here? What is different between them? They are probabilistically the same, so what is different about them? Yeah, it's the information available, right? So the fact that we are here, we know that only two things, if you are at this node, you know you must have a 1 for sure in the next stage, right? Whereas if you're here, well, you could have a 1 or 0, right? If you're here, right, if you stand here, you know that, well, you only have 1, you have 3 1s and 1 0 ahead of you. If you're here, it's different, right? So there is this information. What is the message here? That it doesn't suffice, for this purpose here, it doesn't suffice just to keep the distributions of the random variables. We have to keep the information structure as well. So that's what makes these problems difficult, right? Because it's not just like in the two-stage case where you just have to deal with the distribution of the random variables. No, now we have to deal with the distribution and the information structure behind. right? That's the way to represent those things. That is the values of the random variable, but we need to keep somehow the information about the tree structure. And this makes these multi-stage problems really far more, much more complicated, right? The fact that we have to take this dependence into account. So we need to find some, in order to talk about distributions of these processes, we need to extend this notion of distribution in such a way that it can incorporate the information structure in it. That's the main issue, okay? So again, Flug is one of the most active researchers in this area, right? So he has come up with a distribution that is very convenient for this. This is called this notion of a nested process, right? So what is a nested process? You can think of this as being an extension, right, of the original process in which now what we keep at time t is two components. One is the random vector, right? We always have, that's the value of the random variable at that point. But we also have to keep track of all the conditional distributions up to that point. Okay? You have to keep track of both things. So, I mean, there is, of course, a mathematical definition, but I mean, it's easier to understand from the picture, right? So this is the process that represents this tree here on the left, right? So essentially they're saying, okay, the first stage, you could have 0 or 0, right, the probability half. If you look at the picture, you can see first stage I have 0 or 0 with probability half, right? But if you have this 0 here, right, the bottom 0 is followed by a distribution which is like 0, 0, and then 1, 0, 0, 0, right? So that's what it's saying here. Well, the bottom 0 is followed by a distribution which could be 0, 0 with probability half, and then one that is 0, 0, 0, 1, right? Whereas if you go, this is the upper branch, right? The upper branch has a value 0, but it's followed by another nested distribution, right? That's why it has brackets here. Another nested distribution where you have 0 and 0 is 0.5, right, which was this part here. But then we have 1, 1, 1, 0. And that's what we have, this 1, 1 and the 1, 0. Okay? So this is a way to keep all the information, right? So it's a recursive definition. You can think that way, right? Where this is the values, and then what is below the line are, so this is the probability, sorry. This is the probability of each scenario, and then what comes below it are the values of the scenarios and the nested distribution associated with that node. Okay, so it's a recursive definition. But that's the way to keep track of the whole thing, right? Otherwise, as we said, just looking at the finite dimensional distributions here is not enough. We really need to keep track of the whole structure. So with that, right, with this extended notion of a process, one can define what is called a nested distribution, right? So it's like a distribution on this space of these entities here, right, which are now pairs, right, C's and these conditional probabilities. So, I mean, of course, this mathematically becomes much more involved, but still, conceptually, one can define, right? This, I can define, if I know what my process is now, I can define corresponding notions of distributions, and which essentially means, right, that we work not only with the values but also the conditional distributions. And then we can do the whole thing we did before, right? Define Kantorovich distances, all that business. Now we can apply, right? Because now we have a formal way of defining these tree processes, right? We got the values plus the tree information, right? We just have to move to a different space, but in that space we can do all this again. Monte Kantorovich, everything applies, okay? So that's the nice thing about this work by Flug, right? So he was able, by putting in this context, we can do everything just moving to a different space. Well, but still, how to select the scenario? Our question boils down to this, right? Well, I don't care what space you're doing this, but I want to select the scenarios, ultimately, right? So how do we select the scenarios? Well, so here's one way of doing it, right? So imagine now that we work with this conditional distance. We talk about Wasserstein this, but this could be like the Monte Kantorovich as well, right? general metric distance between the conditional distributions, right? So this is something more concrete, right? So this is what's this? The conditional distribution is, well, if you are here, right? If I'm standing at this node, I'm going to look at this distribution here. What comes later? If I'm standing at this node, I'm going to look, my PT is what's the distribution of these quantities. Okay? So those are, if you look at these conditional distributions, right? Then we can define the, well, if this path, if I look at, I condition the same path, right? So if this path that I'm conditioning on doesn't exist in this tree, I say that the distance is 0, right? If the tree is a subset, right? If this tree is a subset of the big tree. But otherwise, I'm going to look at this distance, this one stage distance, right? Which is the conditional one. So what they show is essentially the following, right? So if I can guarantee that every stage, right? So I look at the distribution at time 1, the one at time 2, right? If I look at the maximum distance for all possible values of xc1, the conditional distribution xc1, the difference between them, right, is less than epsilon, and so on, right? Up to time t, if I look at the conditional distribution, everything that happened so far, right, and take the maximum of those over all possible histories, if I can guarantee that all this is less than epsilon, then I'll say that these two trees are close to each other. So it's kind of strict, right? No, but that's how you guarantee that they are small, right? In essence, this is saying, well, I look at the conditional distributions, and then I'm looking at the other conditional distributions that come here, and here, and here, right? So if I can guarantee that these conditional distributions are closed for the two trees, this one is closed for the other the two trees, and likewise, right? I have two. This is a smaller tree here, right? Let's say I have a smaller tree. And I'm comparing this big one with the smallest one, right? So we're going to look at this conditional distribution, right? Condition that you're standing on this node, this conditional distribution, and comparing with this. And then I look, say, to this conditional distribution, right? What can come after this point, and comparing to this one here, right? So we are comparing stage by stage what happens to the conditional, what's the distance between this guy and the corresponding, this is the process Q, and this is the original P, right? What's the distance between this and this, between this and this, and so on, right? And take the maximum of all that. And so it's possible to show that if this is satisfied, then the nested distributions are closed. What's the nested distribution is the distribution of this Kantorovich distribution for these nested processes, right? It's possible to show that in other words, if I can guarantee that the conditional ones are closed, then the nested ones will be closed as well. So all we have to do now is to generate, to do this conditionally, right? For each realization, we try to do guarantee that in each stage, what we get approximates well what we get from the original tree, okay? So here's an algorithm, right? So let's see how this works in terms of an algorithm, right? So this is the algorithm that, is described in detail in the paper by Flug and Pichler. So for each stage, right, imagine that I'm going to fix the number of scenarios that I want to generate, right? So remember, we have to work with a fixed tree structure that's computationally feasible, right? So let's say, okay, I want to have 5 nodes per stage, okay? 5 children of each node, right? So let's say we fix 5. And then what are we going to do, right? We're going to say, okay, let's look at the conditional distribution, right? So remember, this is our original tree. Let's draw again our, a little bit more carefully, right? So let's suppose that this is our original tree. Could have many nodes, right? And right, this is also a bunch of nodes here, right? Etc. This is our original tree, and then we want to generate a small tree here. Let's put just 2 to make it easier. Right? We want to approximate this large tree with just a binary tree. Okay? So what are you gonna, how does this work, right? It says, okay, fix the number of children. In this case, 2, right? We only have 2 children per node, okay? And then is, okay, so what we're gonna do is say, solve the facility location problem, right? So I want to find, I'm gonna look at all possibilities that I have from my original tree, right? Maybe I have many here, right, for the original tree. Solve the facility location problem. We know how to do that in one stage, right? Or at least in an approximate way. And find what are the 2 scenarios that best approximate this column here, okay? So let's suppose that the best 2 scenarios are this and this. They don't necessarily have to be subsets of these 3, right? Remember, we could do this either as a subset or not as a subset. But imagine that you find these 2 guys. And then we're going to do the following, right? Now I'm going to look at this conditional distribution. I'm going to fix the two children, right? So we have, I mean, if they are not one of the original ones, we merge to the closest one, right? We merge to the closest one, and now we say, okay, what are the, among all the children, how do I represent these children with 2 nodes? Well, maybe it's this and this. How do I represent the children of this? These guys are merged, right, into this. And then I look at all the possible children of them together and say, okay, what are the 2 that represent them well? Okay, then I get this one and this one, right? You see what we are doing, right? So when you fix those 2 scenarios, we have to take those 2 and merge them into this, right? And maybe this one is mapped into this, right? We map the scenarios into the one that is closest to them. And then we have to merge the children, and then the next one is going to be selected from the children together. Okay? And then we keep doing this for all the stages, right? So we find for each conditional distribution, right? Fix this one, and then you look at the children. How the children here is what approximates the children of these guys here, and so on. Okay? So that's how this would work, right? So it approximates the conditional distribution at that node. Well, they also propose an alternative way where instead of fixing the number of scenarios, you fix the precision, and then you find the number of nodes that achieve that precision, right? You can do that by kind of keep increasing the m until you reach a precision epsilon. You can do that, right? So in that way, you guarantee that your final tree is within a pre-specified precision of the original one. Of course, this may be big, right? Then you cannot guarantee that this is small. It could be bigger than what you wished, right? Why we are fixing? Well, so that's why there are 2 alternatives here, right? So in one case, we are fixing the number because you're saying this is what we can do computationally, right? Which is often happening in practice, right? These problems, this tree is what you're going to use to solve the stochastic optimization problem, right? So that's the computational limitation of how large problems you can solve, right? So oftentimes what people do, they say, no, I can only handle 5 branches per node. I cannot handle more than that. Computationally is not practical, right? So if that's the case, you have to fix the number of scenarios. Then you say, okay, I want to find the tree which has only 5 branches, right? That best approximates the original one. Or, just to finish the reasoning here, or you could say, no, I want to fix a precision, and m will be free then, right? That's the alternative. I fix the precision, say, I want to be within 0.5 total distance of the original tree, and let the algorithm find what is the m necessary. But that m might be too large, right? I may end up with a tree that, okay, instead of having like 5 branches here, I have only 4, right? But still might be bigger than what you can actually solve. Oh yeah, no, but that's why we allow m to depend on t, right? Yeah, no, you don't have, yeah, in fact, in practice, normally people take the early ones, you take more branches, and then later you take fewer branches. That's kind of something people in practice do, right? So you do a lot of branches here at the beginning because you have more precision, right? It's a shorter horizon. And as you go farther in the horizon, you do fewer branches because this is far in the future. You don't really know what's going to happen in the future, right? But that's more like a practical recommendation. So this is the algorithm they propose, and of course this requires solving this facility location problem, which is again, right? It's that non-convex problem behind. So they use this stochastic, so this great first order algorithm that finds stationary points, right? But it's at least you can approximate, right? But the bottom line here is that we turn that complicated multi-stage problem into doing the one-stage problem t times, essentially, right? Well, more than t times because for each one you have to do conditional on every branch, right? But still, you only have to do the one-stage problems, which you know how to do, right? Is solving the facility location one. Okay, so another alternative, right, which has been developed quite a bit by the group of Werner Romisch, is to do something that is similar, but apply a scenario reduction technique. Right? Well, what is scenario? Remember what scenario reduction is when you start with a bunch of scenarios and you're just trying to come with a smaller number that represents well those, right? A subset, right, of those scenarios that represent well the original set, right? That's scenario reduction. So one way that you think of this is like, okay, we're going to start we generate a very large tree, right? Which you could do, for example, by Monte Carlo sampling. Right? You could do by quasi-Monte Carlo sampling. You could generate a very, very bushy tree, right, with many nodes, right? And try to, and then you say, okay, I have all these scenarios, and I want to find a subset of all this that represents well my process, right? That's a scenario reduction type of problem. So that's the approach of Romisch and Heitz. Because remember, in Flug's problem, the points that you find don't necessarily have to be subsets of the original ones, right? They could be, the facility location allows you to get other points, but here it's a reduction. So roughly speaking, right, the idea is to find the way you find this for each stage. It's similar to the other one in the sense that you do this conditionally, right? So for each stage, you find the set of nodes that better represent the conditional distributions. Right? We can do this is a combinatorial problem, right, because it's finding subsets. And then we merge the nodes, again, like before, right? As before, we merge the nodes that are closest to the representative one, right? And one nice thing about this algorithm is that you can actually apply in a very practical situation where actually you don't have access to the distributions, right? That's something that, you know, if you talk to people in finance, for example, this happens quite a bit, right? Because they say, well, in finance, all what you have is you see sample paths, right? You see the history of the returns of the process, of your stocks, right? You don't have a distribution of the stock returns. All you see are sample paths, right, in the history. So in this case, you can apply this to sample paths as well. And we're going to illustrate this with the figure, right? So here's how the algorithm works. Yeah, so this is the picture is taken from the paper by Heitz and Romisch. This is a forward construction. How does that work? So here we start with 9 sample paths. Okay, so those are just sample paths from the process, right? There's no tree construction whatsoever, right? Think of these 9 lines here as data, right? You collect nine different sample paths, okay? So now you want to construct you want to make a tree out of those sample paths, okay? So how do we go about it? So this is what they call the forward construction. How does it go? So you say, okay, I have these 9 paths, so I'm going to choose the first one with some criteria. I don't know, take finding one representative. I can do a facility location, for example, right? And find one representative for the 9 ones. Right? I end up with number 5, say. And then you do the following. Okay, now I'm going to look for the 9 nodes here. I'm going to look at, say, what are the two ones that better represent those 9 ones. Remember, we are fixing the structure, right? It's like, I only want two nodes. Okay, you get this and this. And then the circles are, what are the scenarios in the original data that are the closest to this one, right? So these 3 scenarios here are the closest to this one, and these 4 scenarios here are the closest to this one. That's why we group them separately. Is it clear? Right? Now we repeat the process, right? So now we say, okay, now I'm going to look at just these 4 nodes, and I'm going to look at, right, the descendants among the 4 children of these guys. What are the 2 that represent them? Then we get, say, this and that, right? And then, well, look among those 4, we're going to group the ones that are the closest, right? Those are called Voronoi diagrams, right? If you haven't seen that before, right? So this is the closest to this one. This is the closest to this. And likewise here, right? So here we find 3. Instead of 2, we wanted to find 3, say. So this is the closest to this is the closest to this, and so on. So you keep doing this forward, right? So every stage, you solve a facility location problem for the children of that, only for the clusters that you are in, right? So here you have, in the first stage, you have the whole thing. But in the second stage, you do separately for this cluster, and then you do separately for this, and this, and so on. Okay? So you reduce the problem. Okay? This is called the forward construction. They also suggest a backward construction, which is you doing, as the name suggests, you do backwards, right? So we start from here, and then you say, okay, I want to select the nodes that better approximate these 9 guys. Here, the number of nodes could be determined by a precision, right? You fix the precision, and then it finds, like in this case, it selected, say, 7 out of the 9, right? To get good precision. And then you say, okay, now I have these 9 guys. So I'm going to look in the previous stage, out of those 9 guys, or those 7, what are the 4 that better represent them? Or what's the number that gives them an epsilon approximation? And so, right, so out of the 7, we selected this 4, say. Okay? So then we are going to connect. So if you selected this 4 out of the 7, we're going to connect, well, this one was the original children, right? So this one is connected with this one is connected with this, and this is connected with that, because that's the closest one to this, right? And then, again, you do recursively, right? You take this 4 and say, okay, what are the 2 guys that better represent this, best represent this? Okay, those are the 2 ones. So this guy now is going to point to this points to that, this points to this points to that, right? Because this guy is closest. Those are the, right? These 2 are closest to this, and these 2 are closest to this, and so on. You just do it backwards, right? So this way we construct a tree based on the same notion, right? So we are doing this conditionally, always find, okay, what are the nodes that best represent a certain set, and do either forward way or backward way. So it's a different strategy, right? From what Flug did, right? If you're saying the algorithm of Flug was finding what are the scenarios. And here, we're actually starting from particular sample paths and constructing the tree from the sample paths. Okay? We could also have done the same algorithm, but starting from this, right? Doing a big Monte Carlo tree, for example, and doing the scenario reduction using the same principle, right? Either the forward or the backward reduction. It'll work. Wellington?
Which one do you like?
I don't know. I mean, this is an open question, right? I mean, I don't think if you ask a Romish himself, I don't know if he will have an answer, right? In fact, I mean, in that, I think it's either this paper or a subsequent paper, they did quite a bit of numerical experiments, right? With these 2, particularly with these 2 constructions and doing numerically. But the difficulty is a little bit how would we evaluate, right? Okay, if you know the true optimal solution, you can see, okay, which of these problems gave, but maybe it's dependent only for this problem, right? It's not a general conclusion. So it's a very hard question, right? If you think about that. I don't think there's any way you can make a blanket statement and say, no, forward construction is always better, or backward construction is always better. No, because even if you do this for one particular, you study, right, very deeply one problem, and like they did, but still, okay, for that problem, you can say that forward construction is better, but it's just general. I don't know. And I think it really, I mean, both are reasonable, right? So it's hard to say that one is better than the other. So maybe someone should do a paper where they do this in a very comprehensive list of problems, right? Very computational work, right? You test this for problems from the literature, and right? But I have not seen that paper. Oh, but this one has a metric too. Oh, yeah. Remember, all this is based also on that facility location problem, right? Which minimizes the de Cantor of each distance, right? So you can, in fact, that the way they suggest in the paper is precisely that way. When you choose these representative nodes, you fix the precision, and you find how many nodes. That's why you end up with 3 nodes here, for example, right? Because here you needed 3 nodes to represent within the precision that you specified, you needed 3 nodes to get good precision. Right? So yeah, no, you have a metric for the whole thing. In both cases, you have a metric.
And if I'm not mistaken, I think it's in this paper, they also consider another metric to measure the structure of the tree. So they use buff
yeah, they call the filtration distance.
plus the filtration
Yeah,
distance.
and the filtration distance you can see is a cousin of the nested distance, right? It's a way to measure distance. We didn't have time to talk about that here. But yeah, they just that is another way, is a way to measure distance between trees, right? Just like Flug did with the nested ones, they propose an alternative concept, but it's the same goal, right? Of measuring the distance between processes that are represented by trees, right? But that's called the filtration distance. Yeah. So, but you can measure the distances ultimately, right? So you can say, okay, this tree is within, the distance between this one and the original one is, I don't know, 0.4, right? Although, I know, going back to Philip's question, in this case, there is no original process per se. You're just looking at sample paths, right? So the approximation that you're doing here is a function of how many passes you have available, right? It's not like here you could do a very large Monte Carlo, for example, to get a tree and then try to get a subset. So here you could measure the distance between this and the original one. But here, you only have sample paths available. So if you only have fewer paths, like in this case, I only have 9 paths, the best I can do, right, is this, right? I don't have more data. That's impossible to do better than that, right? Because that's the only data I have available, right? But so this is, but still, it's very important in practice because in many cases, as I mentioned, you only see paths. You don't have information about the whole structure of the problem, right? The conditional distributions and so on. You don't have that. You only see paths, right? Only data. Right? Now, if you only have data, you can still do something like this and get a tree out of your data. Right? In fact, Güzin also has work on a problem related to, should let her, she talk about that. Where I think you did some clustering too, right? You had like paths in the water problem. Sorry, I didn't mean to, but you did something like that, right? You had paths from the right. So it was yeah, even those are, if you think about, these are heuristics too, ultimately, right? You try to minimize, of course, you try to minimize the distance, but in terms of the original problem, the optimization problem, it's still, there's no complete guarantees, right? Unless we fall back into the result that, the distance is less than epsilon, we have the stability, but if that distance is not less than epsilon, like in this case, you cannot force this distance to be less than epsilon, right? Because you only have this data available. So strictly speaking, you could not apply the stability result in this case. But so it becomes a heuristic, but it's a good heuristic, of course. Right? It's a good way to construct trees. Okay, so just to finish here, we are in about 10 more minutes. I just want to discuss the one particular, of course, we mentioned this before, right? When the process is stage-wise independent, everything is easier, right? Because all this dependency structure is not necessary, right? You only have a random variable that realizes, right, that has, you only have t random vectors, right? You have xc1, xc2, xc3, and xct. They are all independent of each other, so you don't have to bother about any of this business, right? The tree business. just have independent processes. So this is much, much easier, right? You can apply, say, scenario generation for each stage independently, right? Generate scenarios that way. So it seems that you may say, but this is very restrictive, right? I mean, having this independence is very restrictive, but it turns out it's not so much, right? And we're going to see an example in a second just to show a case where, sometimes you do a modeling trick, to get this. And which, in some cases, it's possible. You cannot do that all the time, right? But in some cases, it works. And we'll see how one situation like that can be done, right? Then of course, right? So if you do that, then you don't have to worry about these conditional distributions. It's much easier. So here's the case, right? So this, I want you to finish up our discussion illustrating a case study, something we did with Erlon Finardi and Vitor de Matos from Federal University of Santa Catarina. And this was a case study for the Brazilian power system. So, of course, this is like just a simpler model of the situation, right? This was a simplification of the actual model that people solve, that people like Joailly has to solve, right? So what's the idea here, right? So let's suppose, right, we had working with hydro and thermal plants, right? And, well, we know that in Brazil, right, as you know well, I mean, most of the energy, a lot of the energy comes from hydroelectric, right? So let's say at some point more than 70%. And so the main thing here is that in the hydrothermal scheduling, right, what's stochastic is essentially the water flows, right? That we don't know how much is going to rain, so that's where the stochasticity comes in, right? And that's a difficulty because you have things that are coupled in time and space, right? The coupling in space is also important, right? Because sometimes the water it's the geography, right? So you have a reservoir here and a reservoir down the river, so what you do here in this reservoir is going to affect what you do downstream, right? So there's dependence, spatial dependence. There's time dependence, of course, right? Because if you take all the water out now, well, you don't have water, right? Next period, the only water that you're going to have is what comes from the rain, right? So the amount of water you have at any point in time depends on the amount of water you had before. The problem is nonlinear. I mean, if you look at the full problem, it's very large scale, right? Because Brazil has many hydro plants and many thermal plants, and so it's a big problem. So the problem here, right, is that you have to figure out how to operate this over time, right? So these decisions are reviewed periodically, right? And you have to figure out what to do, what's going to happen in the future, right? That's why it's a stochastic and dynamic problem, right? You have to figure at every point in time, you have to figure out, okay, how much water I'm going to use for energy and how much I'm going to keep, right, for next time period. Essentially, that is the problem, right? And I want to hedge against uncertainty. In this case, the uncertainty was just the inflows, okay? And then the goal, I want to find a policy that minimizes the expected total cost over the horizon, okay? And the total cost is whatever you get, the thermal costs and some penalties, right, for deficit. In this, again, this is a simplified version. I mean, the full version of this, of course, would include also all the renewable energies and so on, right? But this is just a simplified version of that problem. Then, well, you can look at this model from a long-term, medium-term, short-term perspective, and so on. Okay? Well, that's a classical problem, right? That in Brazil, many people work on that. ONS solves this type of problem, right? So we did some simplifications, right? Some linearizations. The demand, because this is thinking, the goal here was to do long-term planning. So in that case, demand you can actually treat as deterministic because the uncertainty in the water is far, far bigger than the uncertainty in the demand, right? And another thing, simplification here was to reduce the size of the problem that, these hydro plants are aggregated, right, into what they call the energy equivalent reservoirs, right? So you kind of group things together and end up with a smaller number, okay, of the small dimension of the uncertainty. So how do we generate the scenario trees in this case, right? So typically, these water inflows are modeled by a kind of a time series. Remember we mentioned this notion of time series before, right? Where the amount of rain depends on the amount of rain in the P periods preceding it, right? Plus some random quantity, right? This is the random noise, which it has some given distribution. Could be uniform, normal, log normal, right? That's the whole, there's a whole discussion of what's the best way to do the distribution of this guy here, right? I won't get into that. And the phi, right, are coefficients. So this is calibrated with data. I mean, that's nothing to do with optimization, right? So people have calibrated these problems. So, but then, of course, this is the random variables. If you look at the IT variables, they are dependent, right, across stages. Because by definition, IT depends on, is defined, right, in terms of the previous ones. So, of course, they are dependent of each other, right? So there is a dependence. But, well, one can actually make this problem behave as if they were independent per stage, stage-wise independent. How? Well, imagine now that instead of treating the IT as my random variable, I make it a state variable, right? And I do this, so now my uncertainty is really, truly just the noise, right? So if I do that, now I have, I have to add this equation to my model, right? Because now I'm making these state variables. But the advantage is that the uncertainty is just the random. It's just the random noise. So if it's just the random noise, well, it's not too bad to assume that they are stage-wise independent. Right? So that's a key step that is done, which, as you see, it simplifies a lot the scenario generation, but also we can use efficient algorithms. For example, SDDP, which you guys saw last class, right, Wellington? You just saw yesterday, right? SDDP, it's it requires that you have this stage-wise independence, right? So you have the cut sharing and so on, right? So in this case, you can do it. So you can use this type of algorithm by using this, exploiting this structure, right? This stage-wise independence. So if you have that, of course, then doing the scenario generation becomes much easier, right? Because this have to do per stage. So in fact, that paper that I mentioned earlier by Wellington and Claudia uses that idea, right? So they generate they approximate the distribution per stage. They play with that function C. Remember we talked about that function C that measures the distance between two scenarios, right? When taking into account the variance of the process to give a way to generate the scenarios at each stage. Because now you can do stage by stage, right? So in our case, right, so the way, this was the model that we used, right? So that we have some kind of log normal distribution, right? So each component is given by, so this V variable is a multivariate normal, right? So we have some kind of log normal, and this delta are given parameters, right? So this model, again, was calibrated, right, for log normal noises. So, but the bottom line here is that, well, we know the generating samples for C is very easy, right? Because just generating samples from the normal distribution and then apply this. So it's easy to generate samples, okay? So how do we generate the scenarios in this case? Again, the same algorithm we saw before, right? The same type. So we generate these random vectors, right? With the normal random vectors, apply this formula, and then we get the scenarios. And then to get the children, well, they are independent, so we just do stage by stage. Okay, so what I want to show is that, okay, how do you reduce this to smaller trees, right? So you want to have a tree that represents well the original one, right? But you have a smaller number of children for each node. Well, in this case, even talk about a tree is a bit misleading, right? Because ultimately what we have is like for each stage, you have a process, and you want to find a sub-process here for each stage that approximates well, right? So maybe I select this scenario and this scenario. Maybe here I select these three scenarios and so on, right? So this is the original process. And then we want to select maybe a subset of them, right? But per stage, right? So that's what we wanted to do. So the initial one we generated using quasi-Monte Carlo in this case, right? So let's see, then we apply this variable scenario reduction. So I wanted to show some, I mean, it's very limited computational results. It's just to give an idea of how those things behave, right? So all these variable scenario reduction methods. So we compare 6 alternatives, right? So one for a problem with 3 stages, the other is a problem with 5 stages. So we have 2 reservoirs in this case. So it's the stochastic, the random variables have dimension 2, right? Because 2 reservoirs. So for this 3-stage problem, what we did was we had an initial tree of 75 children, right? Generated this with quasi-Monte Carlo. We had 75 children per node. So it's a very thick tree, right? And we wanted to generate one with only 5 per node, right? Much, much smaller, right? You start when it's like 75 for each one, when you get one with just 5, okay? So what are the alternatives? Well, what you did, well, first was the full tree, right? In this case, the problems are small enough. The goal was just to do a computational comparison, right? So we know the full tree, we could solve, right, the full tree. Or let's say we make a random selection on each stage, or we do a backward heuristic for scenarios of the full tree. So here is not that forward construction that we saw, but rather saying, okay, let's look at I have the scenarios in the whole full tree, right? All the scenarios in the full tree. And then I apply the backward and the forward heuristics to see which ones represent these scenarios the best, right? Not that forward construction that we saw, because in this case they are independent per stage. And then and random selections from the full tree, and then the facility location, where you do a facility location on per stage. Okay. So here the type of figures we get, right? So let's understand this figure here. So this is the 2 reservoirs. So this is the 3-stage problem, right? So that's stage 1 and stage 2. So this is the scenarios, the green ones, right? So remember we had 75 nodes per children, right? So you can think of this green graph here as being 75 by 75, right? You have 75 points on each dimension, okay? So the green is the whole thing, the whole tree, right? And the dots are the scenarios that we are selecting. So the random selection, right, from the full tree is just like, okay, I'm going to look at this full 75 by 75 grid and choose 25 points, right? Because you just want 5 points per stage, right? So if I choose 25 points out of this 75 by 75, we end up with something like this, right? For reservoir 1 and this for reservoir 2. You can see that random sampling, of course, right? There's entire areas here that are not covered, right? So random sampling is poor, right? It leaves a lot of holes, right? Like in this case, there is a lot of holes. So here, when you do random choice, the random choice per stage now, right? So say, okay, for stage 1, I'm going to do a random choice. And then for stage 2, also a random choice. Again, right, you can see this is now stage 1 by stage 2, right? So I'm doing random here and random here, right? But now, again, you can get this type of situation where you end up with a very poor coverage of the whole thing, right? Because you're just selecting them random. There's nothing guarantee. The forward heuristic from the full tree, in this case, didn't work particularly well, right? It was too concentrated, right? So here we're selecting out of the 75 by 75 scenarios, right? We are doing the backward heuristic to find the best selection.
What was the function, the distance function you used? The Euclidean?
For the forward heuristic, I think was the Euclidean. We're going to talk about other ones in a second. But the forward heuristic, I think we just used the distance for the vector, right? That's stage 1, stage 2, right? But the backward heuristic now is actually, in this case, did much better, right? So you can see what you're selecting here, right? So it's like out of the 25 by 25, we are selecting exactly these points here, right? So 1, 2, 3, 4, 1, 2, 3, 4, 5, right? Let's see. Yeah, we have 1, 2, 3, 4. Here we have 6. Yeah, 4 times 6, 24, right? We have 4 times 6, 24, plus this extra point in the middle, right? So that's just how you select 25 scenarios out of this 75 by 75 using backward heuristic. Turns out to be a pretty good selection, after all, for both for reservoir 1 and reservoir 2, okay? And those are just the probabilities, but just to give an idea, because this just gives which scenarios are selected, but the figure doesn't tell you what's the probability, right? You can see here, so well, some points in the middle have higher probability. The ones in the tail have very tiny probability, but they still can be, they're still present, right? And this one is doing the facility location with a Wasserstein order 1. Remember, it's like doing Euclidean distance with a power 1. Right, and doing a facility location selection, right? So solving a combinatorial problem for each stage. So you can see a decent coverage here, right? And in stage 1 and for reservoir 1, here's for reservoir 2. And if you look at the Wasserstein order 3, now look at the Euclidean distance to the power 3, it's interesting, right? This is an observation actually that Flug had made that we see it happening here, right? When you look at the Wasserstein order 3, I mean, the comment of the Flug had made is that the higher orders of the Wasserstein tend to get better coverage of the tails. And easy to, kind of intuitive to see why, right? Because you're stretching the distance, right, when you put a higher power. So the result is that, well, when you do a facility location per stage, right? So we're doing stage 1 and stage 2 separately, right? But doing a facility location. So we are finding exactly what are the scenarios that best represent the 75 scenarios in that stage, right? If you use the Wasserstein order 3, then we start seeing these extreme scenarios showing up, right? That's the interesting thing, right? Where this scenario here was the most extreme, was generated, and same here. Maybe not the most extreme, but we start seeing these more extreme scenarios appearing among the generated scenarios, right? So it looks like this is doing a better job than the Wasserstein order 1, for example. And that's, so that's it, right? So this is just to give a small illustration of how, this of course is a very particular problem, but just to give a glimpse of how these things work in practice, right? So this is of course just a two-stage problem, but, and that's what we observed. Yeah, Claudia?
I think when we were doing this scenario selection, it was important to put the weight in the distance. Remember what it was? It was
well, you divide by the variance, right? Something like this. Yes. Yeah. I don't have I didn't do in the implementation of your method. I think you probably would see a lot in the tails if you put for exactly the same example, right? I'm sure you would see more in the tail. Huh? Yes, that was the goal, right? To get a better representation of the extreme cases. That was playing with that C function, right? Essentially, when you play with the C function, you can try to force this extreme cases, because that's an important situation, right? I mean, the extreme cases are the ones that are more problematic, right? Like if you have a big drought, like what we saw, right, in Brazil just last year, right? That there was this huge drought that was months and months without rain, right? And then the big problem, well, how do you forecast that, right? Your planning we should be able to generate these extreme scenarios. It's important, right? You can't ignore them, right? Because they have a huge effect in the planning. That's true, yeah. Although if you have too much rain, I don't think that's much of a problem, right? From this perspective, right? You only have like, well, have more. The more energy, the better, right? Huh? Yeah, it could there be, but from the energy generation perspective, it's not so much an issue, right? What's expensive is when you don't have water, right?
Somehow we are interested in reducing the computing time, and so if we have a lot of emphasis on very favorable scenarios, we are just
What do you mean? I don't understand.
As Felipe said, we have extremes on the good side and on the bad side.
Okay.
Of course, what is important is extremes on the bad side, expensive,
Right.
deficits, and so on. There's the question of studying, but anyway, let's forget about it for this.
Yeah, sure.
But if you come out with scenarios that are favorable, the solving that problem takes simple time, which is useless at the end of the day. Not because it's zero, it doesn't inform us anything in which decision
Mm-hmm.
was taken. So we should somehow put some emphasis on the bad scenarios, not on
because those are more costly at the end of the day. Yes, yes, yes.
I think that we can also underestimate the real cost.
Yeah, because if you never generate these bad scenarios, right, you think that the world is perfect, right? Well, okay, yeah, I have the right amount of rain here. You plan, we're assuming, yeah, it's just going to rain the right amount, right? Okay, in a range, and then this bad scenario hits, right? And like, what do you do? Right? So that's why it's important. So it's an open, right? Actually, it's an open question now, right? How to really, what's a good way of ensuring that extreme scenarios are generated? This is an open question. There are proposals here and there of some methods, but there is no, even this one, right? I mean, if you use a Wasserstein of higher order, but it doesn't really guarantee anything, right? So this is, those are open research questions, right, at this moment. Okay, so just to finalize here, I want you some references. Like I said, this survey that we wrote with Güzin had all the references for the sampling part, all the assessment of solution quality, Monte Carlo methods you can see from the survey. These ones I put here because those are not in the survey, right? This whole, actually, the whole part that we did today about scenario probability metrics is not part of the survey. So those are just some of the references. There are, of course, many more. So I just put some pointers here to some papers, especially recent ones like the ones by Flug and Pichler and so on. But there's a lot more. So from here you can get pointers to earlier papers. It's a very rich area, this whole thing with the probability metrics and etc. So with that, we finish the course. I thank you for your attention. And hope to see you in Buzios next month. Don't forget, right? ICSP.